Hey guys, so let's have a look at this question. So in this question we have a circuit being given. This is the circuit being given to us and all the capacitors are initially uncharged, right? Now we are closing switch S1. After closing switch S1 for a long time, so we are closing switch S1 for a long time. After closing switch S1 for a long time, suddenly S2 is also closed. Suddenly S2 is also being closed over here and that is being kept closed for a long time as well. So we need to find out what will be the total heat produced after closing switch S2, after closing the switch S2 over here, right? So this is a standard circuit problem and hopefully you guys have gone through the video on Kirchhoff's laws because I'll be making use of that to solve this question, right? Okay, anyway, so let me start solving this question. So one way of making this question easy is now when switch S2 is closed. When switch S2 is closed, so this is being grounded and even this is being grounded, right? So let me draw the diagram. So we have a capacitor, then a battery. So I'm drawing this diagram this way. Then we have a capacitor and a battery. Then we have a capacitor and a battery. And then we have a capacitor and a battery, right? And now this is grounded. This is also grounded, right? So one way of imagining this is because both these points are grounded, I can imagine that this is the diagram I have. I can join these 2 points right now, hence creating like a circuit kind of case in this case, a much easier way to visualize this. Okay, so let capacitance, so capacitance is given, capacitance for this is C, this is E, this is C, this is E, so on and so forth. Okay, so now we need to find, in order to find out, we need to find out what will be the amount of heat energy lost after closing switch S2. So let's worry about what will happen after switch S2 is closed. For now, let me deal with what will happen in this circuit at this instant, right? Let me find out the charge on each capacitor, and finding out charge on each capacitor will give me an idea of how much initial energy is there in this circuit, right? And for this, I'll make use of junction law and loop law, right? And the way we'll start off with junction law is imagine that there's a charge Q flowing over here. So let me imagine charge Q is flowing like this. You can start off from any point, it doesn't matter. So let me imagine that I have charge Q flowing over here. So this capacitor will gain a charge Q. This plate will gain a charge minus Q. So because this plate is gaining a charge minus Q, that means that it's pushing plus Q, right? So the charge going over here will also be Q. This will also be minus Q. Then this will be Q. This will also be minus Q. This will be Q. This other plate will be having minus Q, right? And then how is it having minus Q? By pushing plus Q charge outside, and that plus Q charge outside only is coming back over here, right? The grounding doesn't really make a difference over here. Even if you ignore grounding in this case, there won't be much of a difference in this question. It's just a reference point, basically saying that potential over here is 0, right? So not much of a difference over here. We can actually ignore grounding from in this question as well. Okay, so now Q is the only unknown I have in this equation. So now how do I find out what's the value of Q? Since I only have one unknown, one equation will be sufficient to find the answer, and the equation I'll be writing is a loop law equation, right? So let me start from here and let me go across this loop in this manner. Then I'll find out the sum of all potential differences across each element. Sum of potential differences across each element in a circuit when going across a loop should be equal to 0 because I'm coming back to the same point. So the sum of all the potential differences has to be equal to 0. So let me start writing loop law equation, right? So I've assumed plus Q charge is coming over here. So this is your positive plate, this is your negative plate. So I'm going from positive plate to negative plate, which means I'm going from higher potential to lower potential. So potential will decrease. And what will be the change in potential? The change in potential will be Q by C. So because it's decreasing, potential will decrease by Q by C, hence I'm denoting it by a negative sign. That when I go from here to here, the change in potential will be minus Q by C. Next, I'm going across the battery. I'm going from lower potential to higher potential, so potential will increase by E. So let me write it as plus C. Then again, I'm going across a capacitor. Again, I'm going from positive plate to negative plate, so minus Q by C. Again, I'm going across a battery from lower potential to higher potential, so plus E. So hopefully you guys got the idea. So this will be a loop law equation. And this is what happens when I go here, 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 and finally I reach here, right? Now when I go from here to here, no change in potential. When I go from here to here, also no change in potential. When I go from here to here, also no change in potential, because I've there's no element over here to have a potential difference. So now I've reached my initial point. So this is the sum of all potential differences, and now that should be equal to 0. So from this we'll get 4E minus 4Q by C to be equal to 0, which implies I'll get my Q to be equal to C into E. So this will be a charge on each, all the capacitors, if you notice, have the same charge over here. So this will be the charge on all the capacitors. which means what's my initial energy of the system? My initial energy of the system will be equal to 4 times of q squared by 2c. So the initial energy I'll be having over here will be equal to 4 times of c squared e squared divided by 2c, which will become equal to 2c squared, right? So you're dealt with this question for this case. You're dealt with this question for the case when switch S1 is closed. So after switch S1 is closed for a long time, that is when you're letting the capacitors get fully charged, this will be the charge you'll be having on all the capacitors, and this will be the energy the system has, this entire system has. Okay, now let's worry about what happens when switch S2 is closed. So when switch S2 is closed, in this diagram it effectively means that I'm connecting it here. Okay, so let me redraw the circuit diagram and look at what happens in that case. So let me draw the circuit diagram once again. So once again, capacitor, battery, capacitor, battery, battery, capacitor and battery. And now this was the original diagram, but when switch S2 is closed, it's like even this is now connected to the earth. So this is now your circuit diagram, right? Okay, so one thing to notice, our capacitors were already charged right now. So all these capacitors had Q charge, and we had found out the value of that Q charge as well, right? Okay, so now after closing the switch, let's assume that we have X charge flowing into this. So if you have X charge flowing into this, the new charge on this capacitor will become equal to Q plus X, right? And that means the charge on this capacitor will now become minus Q plus X, sorry. Right, so this capacitor was charged initially. So because this capacitor was charged initially, they already had an initial charge, and now X charge is adding on to it. So charge on this plate will be Q plus X, charge on this plate will be minus of Q plus X, which means it's pushing X charge outside. So charge on this plate will also become Q plus X, which means it's pushing X charge outside. Now this X charge which comes over here, that can split into two. So I will have Y charge over here, and I'll have X minus Y charge going into this. So because I have X minus Y charge going into this, now the charge on this capacitor will not be Q. The charge on this capacitor will now be Q plus X minus Y. And that means the charge on this will be minus of Q plus X minus Y. So that means that X minus Y charge is being pushed, and that goes now to this plate. So charge on this capacitor will also become Q plus X minus Y. That means again X minus Y charge is being pushed. So I have X minus Y charge coming over here, X minus Y charge here, X minus Y charge here. And now according to junction law, they will combine, and I'll have X charge coming over here, right? And now you see I have X charge here, I have X charge here, and I have X charge once again over here, right? So hopefully we are once again making use of junction law and loop law to solve this question. And now I applied junction law. I've imagined how flow of charge is happening. So imagine that I've started from this point. You can start your junction law from anywhere. You can start applying junction law from anywhere. You can imagine that X charge is flowing, and then distribute it according to the branches, which I've done in this case, right? Okay, so now I have two unknowns. I don't know the X value, I don't know the Y value as well. So we'll be writing two loop law equations. So let me write loop law equation for this loop, and let me write loop law equation for this loop, right? And I'll start off from here. I'll start off from here and go across this loop. So hopefully you guys have gotten comfortable with loop law. So I'll be writing this equation directly. Your loop law equation for this case will be, I'm going across a capacitor from positive to negative. So minus of Q plus X by C plus E, minus of Q plus X by C plus E. So now I've reached this point. I've gone across this, and this. Now I've reached this point. So now if I go from here to here, no change in potential. If I go from here to here, no change in potential. If I go from here to here, no change in potential. I've reached my original point, which means this should now be equal to 0. So from this I'll get 2E minus of 2 of Q plus X by C is equal to 0. So from this I'll get Q plus X is equal to C. But I already know Q is C, so that implies X has to be equal to 0. That means there is no charge adding on to this capacitor. This capacitor is having Q charge only. This capacitor was having the initial charge which it had here. Right, now let me find out the Y value. What will be a Y value over here? And for that, let me write this loop law equation. So let me start from here and go across this loop. So when I go across this loop right now, what will be my loop law equation? Again, writing the loop law equation directly. So it will be minus of Q plus X minus Y by C plus E, minus of Q plus X minus Y by C plus E. So I've gone here, 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 here. I've reached this point from here. So now when I go from here to here, no change in potential. When I go from here to here, no change in potential. And when I go from here to here, no change in potential. And I've reached my starting point. So I've gone in a loop I come back to my original point. So sum of all the potential differences has to be equal to 0, which means now I'll get 2 twice of q plus x minus y by c has to be equal to 2e, which means q plus x minus y has to be equal to c. I already know q is c, I already know x is 0, so here we'll also get y to be equal to 0, right? And this gives us an interesting conclusion. This tells us that even after closing switch S2, there is no charge flow. There is no charge flow happening. There's no charge flow happening over here, which means whatever initial energy your capacitor had, it's the same final energy which your capacitor system is again having. Your charge on all the capacitor, if you notice, is still Q only. Your Q is still equal to C itself. So your final energy will also be the same. And since there's no charge flow, since initial energy is equal to final energy and there's no charge flow, there will be no heat loss as well. There will be no heat loss as well, right? So we can also argue with this question in a kind of a, potential way by saying that there's no potential difference when you close the switch. But I wanted to take this question as a practice on how you can use KCL and KVL to solve this question, right? So the answer for this will be 0. Hopefully this question made sense. See you guys in the next question.